In this video, we're going to look at some further variation of the shortest path or the minimum distance problem. But first, let's recapture the ideas that we have talked about. So first, we start with this very simple axiom. On a flat surface, the shortest distance, the shortest path between 2 points is the straight line segment. So given 2 points on a flat surface, the shortest path moving from A to B is going to be the straight line segment from A to B, which means that for any other path, including this path, the distance of this walking from this is going to be bigger than this. And that's the basis for the triangle inequality. Or a path like that, that's also going to be bigger than this path, which means that in a quadrilateral, the sum of any three sides is going to be bigger than this side. Or a curve like that. This path is going to be longer than this A and B straight line. And in a previous video, we also talked about this problem of building a station for two schools such that the sum distance is the smallest. And there are two cases. Assuming the road is in between two schools, and we have two schools A and B, we're going to build a station such that the sum of the distance, let's say the station S, the sum of SA plus SB is the smallest. And we know that SA plus SB from the triangle inequality is going to be bigger than AB. And if we pick up the station to be at the crossing point of S star, then the sum distance for the station between A to this station and B to this station is going to be AS star plus S star B is going to be equal to AB, and that is the smallest. So for two schools on the two sides of a road, let's say this is a road, then the station is going to be built on the cross point of connecting this AB line with the road. That will give you the smallest distance. The second case is more tricky. What if the two schools on the same side, A, and the other school is B, and we want to build a station here such that the AS plus SB is the smallest? And for that, we use a really good trick, because thinking about this road, we can make a reflection of SB to the other side of the road. If we make a reflection of B to the other side of the road, B prime, so that this is really a symmetric point. So B just keep the same distance and reflect the same distance to the B prime, then SB is going to equal SB prime. So now the problem changes into I want to find S such that AS plus SB prime is the smallest. Or a different way to put it is I want to find a station on road such that the sum of AS plus SB prime is the smallest. But that's exactly the same problem as the first problem when the two schools on the different sides of the road. So in that case, the station we're going to build is just connect A to B prime. The cross point will be our best station point, S star. And this idea is called reflection. And the key point here we're trying to make is really we want to make a transformation such that the SB, the distance not change, and change it to SB prime. And now the problem becomes a problem of the two schools are on the different sides of the road and where to find the station on the road such that the sum of distance of SA and SB prime is the smallest. So the key is to do an equivalent transformation and transform the problem into a simpler problem or a familiar problem. In this video, we're going to look at another variation of the same idea. The same idea of using an equivalent transformation so that the problem becomes a much simpler problem. Okay, the problem goes like, there's a river between two small villages A and B. Where to build a bridge on the river so that the path from A to B is the shortest. So when we say the path is, we're basically going to build a road towards the bridge from both villages. So I'm going to draw a graph to represent the idea. Let's say this is the river, and there's a school A, a village A, and there's a village B. And we want to build a bridge somewhere, let's say here, this is the bridge, which we're required to be perpendicular to the river. And we're in here, we assume the river has equal distance everywhere. Okay, that's a kind of abstract of the math idea, of kind of abstract of the actual physical world. And we're going to build a road from A to the bridge and B to the bridge. Okay, does not matter where you build the bridge, I'm going to just connect from B to the bridge directly and from the bridge to the A also directly. But here the question asks you how to find this bridge such that the sum of the distance, let's call this as x and y, the bridge is x and y, so that ax plus xy, the bridge then, plus yb is the smallest. This is, of course, the path distance from A to B. So where are we going to build a bridge? And surely the bridge is going to be determined by, the relative point on the river. You can parallelly move this bridge, right? You can build a bridge maybe here. And then the path will be this one, and plus bridge. The question is where you're going to find the location of the bridge. So give yourself some minute to really thinking this question. Assume that you have spent the time. Let's see how we address it. So first of all, we realize that this xy is really irrelevant because xy is always the distance or the width of the river, the span of the river. So xy is a constant. So really we want to find somewhere a place so that ax plus yb is the smallest. Okay, does that really help? Not so fast. But the thing is, when I do the by plus ax, the ax is actually, I'm going to do a equivalent transformation. I'm going to build a parallelogram. I'm going to bring down the a to a prime. So basically, if the distance of the river, the span of the river is d, I'm going to build a parallelogram of xy a prime a. This is also d prime. So this is a parallelogram. So in here, ax is the same as a prime y. Yeah, because this is the parallelogram. I bring down a to a prime. Now the question becomes, I want to find a point on one side of the bank such that by plus ya prime is the smallest. And the question, of course, is where to find a y, where the y should be. Now do you see, is this problem familiar? This is the same problem as I have two squares on two different sides of the road, and where I'm going to build a station S star such that A star and star B is the smallest. So in here, when I bring down A to A prime, really the Y star it should be connect B to the A prime. This is the best location to build a bridge. And the best distance will be I connect B with the A prime, cross this bank of the river, and this is the Y star. And then I'm going to build a bridge here, and this will be X star. And the shortest distance will be B, Y star to X star, and then X star to Y. And that's we're going to build a bridge. And the trick of solving this problem is, again, an equivalent transformation of the distance, the original distance, AX to A prime Y by building a parallelogram. And this is, in spirit, very similar to the reflection principle. Change the distance to another distance, and that problem becomes a much easier problem to solve.